aboard. How you doing there, Antic? Hello there, Bester. Glad to have everyone here with us today. What's everybody doing today? Hope we're doing okay. Let's get some bass in here. There we go. A bit of sodium hydroxide base to give this some color. Looking nice. Yeah. How you doing there, Ash? Welcome aboard. Got some experiments ready for everybody today. Lots of good experiments ready for us today. Let's add a little dry ice to this mixture, shall we? Huh? Get things started off right today. Get a little piece of it here. Here we go. A little dry ice. Yeah? We're going to pop it in this purple thing right here. Let me get a smaller piece. There we go. Slightly smaller piece. Need a hammer is what I need. There we go. All right. Hey, great to hear it, Ash. Congratulations. Here we go. We got a little bit of dry ice here. We're going to add it to this container, which is at pH 10. Let's see what happens when the dry ice goes in there. Not much, huh? Just a bunch of cloudy goodness. Oh, look at this. We're at blue. We are at aqua, now green. Like a greenish yellow. Thank you there, you're not forgotten. Thank you there, Ash. Yeah, we're at like a yellow now. So yeah, carbon dioxide's an acid, and dry ice is carbon dioxide. So when you add dry ice to this flask, it's going to bubble carbon dioxide through it, and it's going to lower the pH. We're down to about pH 6 right now. Nice yellow color. We'll let that continue to bubble through. It's kind of cool to watch. Just going really fast. Wish I could do a slow-mo. Yeah, it's not carbon monoxide. This is carbon dioxide. I would not want to be putting a some solid carbon monoxide in there. Before the dry ice, you are not forgotten, there's some water in the flask. And to the water, I've added some universal indicator. It's also known as rainbow indicator. It displays these colors at different pH values. So right now we're like a little bit orange yellow, so we're just below pH 6. Anything that's a pH of 7 is going to be neutral. Anything below pH 7 will be acidic. Anything above pH 7 will be alkaline or basic. That has a slight reddish color to it, so I know we're down maybe around pH, 5.8, 5.9, somewhere in there. Maybe 5.5 at this point. And that's because carbon dioxide, which you can see bubbling through there, carbon dioxide, when it dissolves into water, it forms an acid. People like to call it carbonic acid. I'm going to go ahead and add a few drops of base to our mixture now. Here we go. In goes a drop of base. You can see the color shifts to a green because now it's kind of yellow. Let me add another drop of base. So as I add the base, it neutralizes the acid that's present. But there's a lot of carbon dioxide dissolved in the water. And so even though that might go to like a bluish color, as the carbon dioxide that's already present continues to react, it goes back to a yellow. Alkaline water is not, that's just a marketing gimmick. Alkaline water is just a marketing gimmick. It might be slightly better for your teeth. Let's see how long this is going to last, aqua. Remember, there's a lot of carbon dioxide that's been bubbled into this solution, and it reacts slowly. You're welcome, you're not forgotten. It slowly reacts with the sodium hydroxide base that I'm adding. Let's add a bunch. See if we get to like a purple or a blue. There we go. Let's see. So we got it all the way back to purple. So the pH is like a 10 now. Now it's blue. You can see here the pH is dropping, right? We're at like a pH of 9. When it gets to aqua, which is slowly approaching, it's like a pH of 8 now. And as the carbon dioxide continues to react with the added base, we might get this to a green color. We might neutralize it. It's a slow reaction between the carbon dioxide and the sodium hydroxide. Very slow reaction. Kind of cool, huh? Let's get the spinner going, huh? Get the vortex going. At the same time, we got some dry ice in there, man. Is there any explanation for my nose feeling like it's burning when you drink carbonated drink? Sure, Ashmaster, what's going on there is, you know, carbon dioxide is, you know, it's poisonous for the body, relatively speaking. And so, you know, when you, you know, it's an acid. So when that stuff dissolves into the water in your mucous membranes, you're going to get some acid in there, and your body's going to, it's not going to like that. So there's some sensors there to tell you that, hey, I don't want to be using this stuff. Get away. Like, I think humans are the only mammals that will drink carbonated beverages. We got an interesting tornado. Pardon me, it's like a bubble tornado. Look at that. That's kind of cool. Yeah, it's like a bubble tornado. It's kind of interesting. Oh, there it goes. The CO2 that's dissolved in there is reacting with the base that I've added. Let's add a few more drops here. Very nice. All right, the dry ice is almost gone. I can see just one little piece of it left. It's kind of floating around. It's almost done. But I can see a bunch of the bubbles right through there, man. Let's add a bunch of base here. There we go. Interesting. All right, let's start adding some acid now. Here we go. Add acid back. I'm adding drops of acid now. Boy, it's taking a while. It looks like the system's buffered now. That just means a buffer is a system that resists changes in pH. I'll slow this down a bit. There we go. Add a few more drops here. A couple drops. Yeah, that is really well buffered. Let's get this thing started from the start, all right? We'll take it up from the top. So I'm going to go ahead and I'm going to get, let's see. Let me get one of my flasks ready here. Let's use this one. This one's an interestingly shaped one. And we'll fill this with some water. So we'll get this one filled with some water. Put this back here so we can see our little, there we go. All right, let's get some water in there. Where is my container of water? Right here. Let's fill this baby up. So you can see how this goes from the start. In goes the water. That's probably enough. Let's get a stir bar in there. We'll get a magnetic stir bar going in there. I don't think it's quite like insulin resistance. I would think that's probably something else. Okay, let's get a stir bar in here. Get this stirring. So I'm going to put this little magnet. It's a plastic-coated magnet. It's going to go in here. And then you can see it down there at the bottom. Now I'm going to turn this on. It's a little spinner. It's a magnetic spinner, and that's going to make our little stir bar spin. And that should get us a vortex going there in the middle. It should. It'll take a little bit. It did look a little bit like a pill. And then we're going to add some universal indicator. We're having a hard time getting the vortex going. Is there even a vortex there? Yeah, I see it. Can you see it up there at the top? Right up there. We got our vortex going. Let's start adding the universal indicator. Down here at the bottom, you can see the different colors that universal indicator displays at different pH values. So let's check out what the pH of our water is. See, the universal indicator starts out green or neutral. I'm going to add some here. You'll notice that it generally stays in the center of the vortex. That's because just like the eye of a hurricane is low pressure, the eye of our vortex is also low pressure, and material tends to stay in a low pressure region, right? Material moves from high pressure to low pressure. Thank you there, Mango. All right, let's add a little more universal indicator. We're going to add quite a bit. It's beautiful, isn't it? That tornado kind of stays focused in the vortex center. One more. Get some interesting flow patterns. I think we can add a bit more still. It's like a lime green color. It is beautiful, Mango. I agree with you. A little more here. All right, we'll leave it there for now. Got a nice green color. That's neutral, right? So you can see our pH is neutral. Now I'm going to start adding, let's add some acid to this. Here we go. Here we go, baby. Come on now. Add a couple drops of acid. There we go. 1, 2, 3, 4. And looks like we're no longer green. I see some red in there. Let's see where the pH is going to equilibrate to. It looks like a yellow color, so our pH is 6. Let's add a few more drops. The acid that I'm adding is hydrochloric acid. It's the same acid that's found in your stomach. It's just that this stuff is like, 100 times more concentrated. Looks like now we're at like a pH of maybe 5. Of course, it hasn't completely equilibrated yet. Let's add a few more drops. Looks like a fire in a bottle, baby. Fire in a bottle. Can pH 5.5 give you chemical burns? Probably not from the pH alone. That's what we're going for, Mango. A little bit of art, a little bit of science. Here we go. A couple more drops of the acid. We're down to like pH 3. Really low pH. I'll turn this light on so you can see it. pH 3, yeah. Nice red color. And now what we do is we add some base, baby. Here we go. Hello there, Alex. Welcome aboard. Let's add 2 drops. No, I'm going to add 1 drop. See what happens. I'll add a second if I need to. Look at that. Think we got a little rainbow action. Little rainbow. Come on, baby. Come on now. Hey, Alex, I'm not sure I understand the question. Does it hurt the protons? That's a gorgeous rainbow we got going in our vase there. Thank you there, Kim. Let's add a few more drops of base. You'll notice that this is going to shift to a more... Probably not, Bester. That's up to you, man. There's no science to that. That's cool, Mango. Me too. That's a good one. That's a good one. Here we go. Another drop. All right. Let's add a few more drops of the acid. Send it back in the other direction. We're at like pH 10. Let's add some drops of acid here. See what happens. You can see that red color grow in. Where's it going to land as the acid and the base react with each other? I'm going to add a few more drops here in the middle. Make it looking pretty. Sure, go ahead. Give that screen a double tap if you want. Let's go a few more drops of our acid, hydrochloric acid, same acid that's found in your stomach. We're going to get that nice and fiery red, indicating a pH of about 3. And then we're going to start adding some base. Come on, man. Give me the rainbow. Come on, you can do it. Let's see. The rainbow urn. There it is, a little flash of it. Excuse me a second, I got a little bit of that acid on my fingers. I got to wash it off. Just a bit. There we go. All right, wash it off. Thank you there, Kim. I appreciate that. How acidic is stomach acid? So, Ash, stomach acid is usually about a pH of 1.5 on average. Now, of course, that's going to vary widely from individual to individual. It'll also vary, depending on what you eat. But that's, on average, what the pH of the human stomach is on fasting. The pH of this stuff is negative. It's so low, it's negative. Bester, I don't know. It's just a glass vase. I couldn't tell you what kind it is. How you doing there, Mike? All right, Mango. Mango wants the purple. We're bringing back the purple because Mango wanted it. Here we go. To get back to purple, right now we're like pH, down here we're like pH 3 or 4. And now I'm going to add some sodium hydroxide to increase the pH. There's 1 drop. Boy, that's gorgeous. And that may be all we needed, man. Well, we didn't quite get to purple. It looks more like an aqua, so I'm going to say we're like pH 8. Let's add another drop of base. Ike, 85. I don't see the particles that you're referring to. I apologize. So I can't answer the question. That's true, Ash. It's glasses tend not to react with acid. Hydrofluoric acid does react with glass. All right, we got a really high purple pH. pH 10 or higher. pH 10 or higher. I'm going to start adding drops of acid, okay? So here we go. First drop of hydrochloric acid. That's the same acid that's found in your stomach. It's just the stuff I use is a lot more concentrated. Thank you there, Mango. So that's our first drop. Let's add another drop. Oh, that's 2. I added 2 drops. You can see a little bit of the red up here, just a bit. This is very basic. Let's add another drop of the acid. 1 more. We are still stuck at pH 10. Come on, man. Something's got to happen here. Let's add another drop. I'm going to go 2 drops. No, I'm going to go 3. So there's 3 drops of the acid. You can see the red where the acid has gone in. It's starting to react with the base. Looks like our pH is down to maybe a 9 or an 8. Probably 9. Can you drink pH 12 water? It's about getting to the point where I wouldn't. Mercury hydroxide, Bester, that's going to depend on how much mercury hydroxide you would dissolve into the water. It is also going to depend on, mercury hydroxide, a lot of metal hydroxides, which mercury hydroxide is, a lot of metal hydroxides do not dissolve very well in water. So the pH of that particular mixture, if you put some of that solid into water, it's going to depend on how much of the mercury hydroxide dissolves. And I don't have that. There's a certain value we use. It's called the solubility product constant. It's abbreviated with a capital K and a subscript little s, little p. And the higher the value of KSP, the better the salt dissolves. And so what you would say is the higher the value of KSP, you'd get more hydroxide dissolved, and that's going to give you a higher pH. If you've had chemistry, you might know what I'm talking about. Cool there, Ash. All right, here we go. How does that, if you don't mind us asking, how does that manifest? How does that manifest for you? Look at that gorgeousness there. That was a cool little green fading to like a orange-red sunset. Let's add another drop of base. There it goes. Adrenergic arousal. I don't know what that means. I apologize. So you're heightened. I think you might have meant arousal, but I'm just guessing. Bester, I don't know. I apologize. You might define that for us, help us out a little bit, but if you don't want to, that's okay too. Thanks there, Mango. I can too. It's kind of fun. It's kind of, I don't know, just kind of peaceful. A couple drops there, a little more acid. Let's add some base. See if we can get that rainbow, folks. Come on now. Come on, let's go. 1, 2 drops of base. Let's see what happens here. Oh, I think I added too much base. That's too much base, man. That went to a high pH pretty quickly. All right, let's get the pH back down again. Let's add some acid here. Clean up that base, baby. And we're going to try again. Come on, a little more in there. So John Doe says they heard that fluorine has 9 valence electrons. So John, what you probably heard is that fluorine has 7 valence electrons. It has 9 total, but it has 7 valence. Is that why it's so reactive when it's part of a molecule? Got it there, Ash. Thanks. So, John, what's going on with fluorine, with why it's so reactive, is it has what we chemists say is a very high effective nuclear charge. So all atoms have a nucleus, and the nucleus is positive. Okay? Now, when an electron approaches, now electrons are negative, so electrons are going to be attracted to the nucleus. Electrons are going to be attracted to a nucleus that's more positive. But here's the deal. In atoms, there's electrons and there's protons. So the electrons in the atom get in the way of the proton, the nucleus. All right? So here's our nucleus, right? Big and positive. There's electrons out here, right, that are attracted to this. Now, some atoms are very reactive, and nonmetals are this way because the nucleus is good at attracting electrons to itself. Now, how much the nucleus attracts electrons has to do with what's called the effective nuclear charge, and that's the balance of the charge on the nucleus and how close the electrons can get to it and how much the electrons that are already there shield or keep new electrons away. So a large positive nucleus, electrons that can get close to it, and few electrons that can shield, that conspire to an atom being able to really pull in a lot of electrons to itself. That's really complicated, but the way we chemists try to simplify it is we have this measure called the effective nuclear charge. That's basically how big positive that nucleus appears to electrons that want to get to the nucleus. And fluorine has an enormously high effective nuclear charge. It also has a high electronegativity, which is similar. So that's why fluorine tends to be highly reactive. It's like an electron eater. So Bester says, adrenaline surges through the day. Wow. That sounds like a mixed blessing, Bester. I don't know. What happens if the electrons get too close? So Bester, the electrons can't get too close. This is kind of remarkable. This is a kind of remarkable fact about the electron. So the electron can't get into the nucleus. They cannot crash into the nucleus. They have associated with them a quantized, we'll just say a quantized, what they have is a quantized orbital angular momentum is what they have. But we'll just say they have to exist in energy shells that are outside the nucleus. If they were to crash into the nucleus, you'd have a very small particle in a very tiny area. And quantum mechanics tells us when we get really small things into really tiny areas or volumes, the energy just skyrockets. And so if you were to trap the electron in the area of the nucleus, you would have a very high energy, extremely unstable entity, which would just fall apart. Kind of cool, man, isn't it? All right, let's move over to this experiment here. Let's do this one. Let's do the separation. All right, sure, man. All right, so what we got over here? Let's add some alcohol to this. We already have some water in here. We're gonna add some alcohol, okay? we're gonna do the separation experiment. All right, so water's in here. We're gonna add some isopropyl alcohol, and it goes. So I got my funnel up here. Come on, Mango, here we go, baby. Come on, in it goes. In goes the alcohol. That's probably good enough. All right. And it looks like you can see 2 layers. Yeah. Let's zoom in on it. I'll turn this off so we're not listening to it. You can kind of see 2 layers. I'll turn this off. Maybe we can see it better. Yeah, look at that. You know, you see all the bubbles that are coming from the mixing of the alcohol in the water. And maybe, I don't know. I can't tell if there's 2 layers in there or not. Let's go ahead and cap it off and mix it up. See if the alcohol and water mix. Excuse me. Organoson was made. I think that was made by slamming calcium into californium or something like that. That might be right. Something like that. All right. Anyway, looks like we've mixed it up, right? We've mixed together the alcohol and the water. And you see a bunch of bubbles, and that's just because the alcohol molecules and the water molecules pack together, and they pack together tighter than those molecules do regularly, and so a vacuum's formed, and that's what makes these bubbles. And those bubbles are going to dissipate. They're going to go out to the top. All right, yep. Okay. Now what we're going to do is we're going to add some salt to this. We're going to salt out the... I'm just trying to get the lighting a little bit better for us here. We're going to salt out the alcohol. So what happens when you add some salt to a mixture of water and alcohol? What happens is the salt ions and the water molecules attract so strongly that they, what I like to call, they date exclusively. So, you know, just like when 2 people meet each other and they're very attracted to one another, they kind of decide that they're just going to see each other exclusively, right? They're going to date exclusively. Sometimes they promise, you know, stay together forever in marriage or something like that. Hello there, Kim Jong. And so it's going to stay mixed there, Jacob. So if I let it sit after mixing, it's going to stay. All right? Protons and electrons are like the same sides of a magnet. So they have electric charge, Bester. Hey, happy Sunday, Future Farm. Okay, so we've got water in here. We've got alcohol in here. I'm now going to add some salt. And when I do this, the salt dissolves, and that makes a bunch of ions. And those ions, interestingly enough, they become very attracted to those water molecules. The water molecules and the salt ions, baby, they love each other. They get so strongly attracted to each other that the resulting salt-water mixture will not allow any alcohol in. The attraction between the salt ions and the water molecules is so strong that the alcohol gets pushed out. Now, alcohol is less dense than salt water, and so you'll see here, we should get a salt water layer on bottom. Let's see if I can see it happening. I think I can. I can tell it's happening. You can see the alcohol layer up here. I see the salt water layer on bottom, and in the middle, there's a transient mixture of salt water and alcohol. We call that the emulsion. You can totally see there's 2 layers, right? The separation is like right there. It's a little tough to see, but there's your separation layer. So down there on the bottom, we've got salt water. Up there on the top, we've got the alcohol. So the salt and the alcohol, the salt and the water mixed together so strongly that it forced the alcohol out. It's all right, Bester. Hey, just ask questions for whatever you don't understand. What happened if you did this under vacuum? probably everything would boil. Let's give this another shake and see if we can see the separation again. We're going to add some color then, because you can really see what's going on if you add some color. But let's just give this a shake here. All right, there's our shake. All right, let's see what happens here. You should be able to see a clarified alcohol layer on top. In the middle, there's a mixture of salt water and alcohol. We call that the emulsion. And down on the bottom, you can see the salt water layer pretty easily. You see that layer right there. So this emulsion is shrinking over time. And we'll see where that layer ends up. Absolutely you could, Jacob. You can use salt to remove alcohol out of water. And unfortunately, there is a little bit of salt that's going to remain in the alcohol layer. But I'm not sure how much. Okay, let's add some color to this, shall we? Put a rainbow in the chat if you would like to see universal indicator added to this. I also have some food dyes. I have some violet food dye. I have all sorts of different colors of food dye. If you just like to see food dye added, put the heart emoji with the color of the heart of the food dye you'd like to see me to add. So if you want to see yellow food dye, put a yellow heart. If you'd like to see me add universal indicator, then pop the rainbow in the chat. And I'll read some comments, take some questions as folks are getting in their votes. What would happen if we use sugar? Bester, great question. I wish I had some sugar down here so we could try it. Boy, those two layers are showing up really nice. So Malto is asking for either universal indicator or orange dye, which would be a drop of red and a drop of yellow. Any other votes? Right now, Malto would adding salt to a bottle of vodka remove the water from the vodka. Yes, it would remove the water from the vodka, I am Josh. It would do that. Now, here's the deal, Josh. I'm not sure if, the salt is mostly going to go into the water layer, but I think you're going to get some residual salt, unfortunately, into the alcohol layer. I'm not certain of that. It's something that you could test and try to get the ratios right to where you could get the separation, but not the salt and the alcohol. Jason saying green. Linus was going to ask the same question. So right now we got to vote for orange, we got to vote for rainbow, we got to vote for green. Come on, man, I want to do the experiment. Get your votes in, folks. Get your votes in. Let's see, ask a question. What color should I add? Rainbow or other? Start the poll. What color should I add, folks? What color should I add? Rainbow means universal indicator. Then how could you remove the salt from the alcohol? Yeah, Jake, I don't know, man. I'd have to think about that. So Josh is saying add blue, Future Farm. Not going to happen there, Future Farm. We got another vote for green. All right, we're doing green. I saw 2 votes. Oh, Jacob came in with a late vote for the rainbow, ultraviolet. All right, here's what we're going to do. We'll do a couple of these, all right? Let's add universal indicator first. So that's what I'm going to add first. All right. I'm going to take the poll away. Thanks for your votes. Get it out of there. Let's add a little universal indicator here, folks. Oh, yeah. 4265 wants some pink. What would happen if you added yeast or flour or baking powder? I don't know, Bester. Here we go. In goes the universal indicator. Let's give it a good squirt here. And it goes. Look at that. Isn't that cool? Isn't that cool? It looks like it pretty much floats on the alcohol layer, huh? Actually, look at that. Look at that. It's not penetrating the water layer, the salt water layer. Isn't that cool? Come on, man. That's cool. Yeah? Okay, now we're at like a pH of 6, right? You remember this? So universal indicator tells us we're at pH 6. Yeah? Yellow is pH 6. It is crazy. It's cool, isn't it? Now what we're going to do is we're going to shake this up and see what happens. Because, we're going to find out. There's actually 4 different dyes in the universal indicator. Right now, it looks like all of them kind of preferentially go into the alcohol and no go in the salt water, but that might not be the case. Let's shake this up and see which layer the dyes in the universal indicator go. Hello there, Bree. Welcome aboard. Thank you there, Peace. Thank you there, Malto. Here we go. Let's shake it up. Maybe it'll end up in both layers. I don't know. We're going to find out. That's why we got to do the experiment. So here we go. We're going to shake this baby up, and we're going to check it out and see. Now, it's easier to see the layers now. You can see the alcohol. Holy cow, look at that. Come on, man. None of it ends up in the water layer. Look at that down there. See that little water layer down there? Well, maybe a little bit. That's got a little yellow tint to it, but it's real easy to see the emulsion now, right? The emulsion is the mixture of the alcohol and the salt water. Isn't that cool? Isn't that cool? Very beautiful. What's fun about universal indicator, somebody said they wanted to see green. Well, we can make green with universal indicator. Here we go. Watch how we're going to do this, right? Because we can get all the different colors. So check this out. All right, let me get this back on. So you might remember universal indicator can display all the colors. Right now we're at pH 6. So I want to get to green. That means I got to get to pH 7. I got to add some base to increase the pH. All right, so that's what I'm going to do next. Let me read this question first. Would a simple filter or coffee filters filter out the salt? No, simple filtering will not filter out the salt. You're going to have to redistill it, unfortunately. Because the salt is dissolved into, it would be dissolved into the alcohol. Let's give a little, so explain, FYU. What's happening here, FYU? There is salt water down here, alcohol up here. Those two don't mix, okay? I've added some dye to this, and we can easily see that the dye dissolves in the alcohol layer better than the water layer. Now, the dye happens to be a mixture of dyes that show these colors at different pH values. We can easily see we're at pH 6, which is slightly acidic. Folks wanted to see green, so I'm going to add a little bit of base to see if I can't get it to pH 7. I'm not sure this is going to work, but we're going to give it a shot. So in goes a drop of base up here at the top. You'll see it go in. Boop. There it goes. And you can kind of see the color, right? The base is going to make things shift to a blue. You can totally see the result of adding the base. Why don't they mix? They don't mix, Malto, because the salt and the water molecules are so strongly attracted. They, just like people when they're strongly attracted, they date exclusively, so to speak. So the attraction between the salt and the water, the salt ions and the water molecules are so strong that the alcohol can't outcompete those attractions. So it gets forced out. Here we go. Let's give this a little shake. Thank you there, Peace. That's what we're going to do, Niall. Niles, here we go. We're going to give that a good shake. And there's a green. Wait. Oh, I overshot. I went to blue. Sorry about that, folks. It's a little too basic. Let's let that set there and see what's going on now. So now our pH is pretty high. We're like pH 9, maybe 10. More like 9. Whoa, but look at this. Come on, baby. What the heck? So you might remember I told you that the universal indicator has more than one dye in it. And what's really happening here is we're like a pH of 10, which is violet. The blue and this pink color give you the violet, and it turns out that the blue color ends up in the alcohol, whereas the violet ends up in the salt water. Isn't that interesting? It's a really interesting effect when this happens. Hey, Brian, help me out. Tell me why that's not super safe. Is that just because you end up getting a little bit of salt in the alcohol, and then, it's not really good to drink salt? Hey, thanks there, Jenna. I appreciate that. All the way from Europe. I love it. Can I try to put cooking oil and alcohol water and something else? Neil, I don't have those ingredients, unfortunately. Hello there, Angel. It looks like magic, Bende, but it is science, baby. No, Peace. It's not salt water that's pH 10. I am adding some sodium hydroxide that's like much higher than pH 10. Okay, now we're going to add a little bit of acid to this. I'm going to add a little bit of acid. Here we go. That's going to lower the pH, right? What's fun when we add the acid? This is kind of neat. So in goes the hydrochloric acid. 1, 2, 3, 4. Let's do 4 drops. Can you see it? Can you look at that? I can see it. It's kind of like the day breaking on the horizon. So as the acid, which is, that's going to be a low pH, pH 3, red, you can tell that the acid solution that I've added is more dense than the alcohol, but less dense than the saltwater layer. Yeah, that's salt water sinking to the bottom, Jacob. That is definitely salt water that's more dense than the alcohol, so it sinks. Here we go. We're going to shake this baby up. Let's see what happens. So we got a lot of base in here, but I've also added a lot of acid. Now, when I shake this up, if the acid and the base completely neutralize each other, we'll be at pH 7. If there's more acid, the color will look like this, red, orange, or yellow, depending on how much acid is left. And if there's more base, it'll either be aqua, blue, or violet, depending on how much base is left. Here we go. Let's see what happens. I don't know if there's more acid or base in here, but after we shake it up, we're sure going to find out. Here we go, baby. Here we go. Looks red. Looks orange. Looks like we're going to end up with orange. I think that's like a pH of 4 or 5. If you don't put alcohol, will the universal indicator mix with the salt water? Yes, it will, Malto. I mean, that basically over there is salt water with the universal indicator. Look at that. That's gorgeous. Very pretty. Mark. I get plenty of trolls anyway, too, Mark. You guys keep it interesting, I'll tell you that. Hello there, SS. Wait, so if the purple was taking over the blue, why would you see blue in the purple? So here's the deal. Here, let's make it the purple and the blue again, okay? Thank you there, Peace. Yeah, consider liking, sharing, subscribing. If you like this kind of thing, if you like science experiments, I got, my channel's Tommy Technetium. I do a lot of science experiments. I put out at least one short form video a week. It's sometimes a deep dive into some chemistry. So Jingling, what we are doing here, you guys let's start from the beginning. I'll start from the beginning and we'll start the whole experiment from the beginning so you can see what's going on. Here we go. Why is it separating? We'll answer all these questions, okay? So what I have here in this bottle is some water, all right? That's all that's in there. And now what I'm going to do to this water is I'm going to add some isopropyl alcohol. So here we go. In goes the isopropyl alcohol. Hey, thanks for hanging out, Malto. It's great having you on board. Appreciate all the questions and had a good time with you. So here we go. For folks that want to know, we're going to put some isopropyl alcohol in here. So this will now be a mixture of isopropyl alcohol and water. Once I get it all in there. Okay. There we go. Ah! I hate it when that happens. Sorry, folks. Give me a second here. Dadgummit. Oh, I added too much. Oh, rats. All right, give me a second. Shoot. Curses. Curses, curses, curses. This is going to take me a second, all right? I'll be all right, though, here. Just going to take a second. I would just want to... Oh, man. I forgot. I forgot to pull the nose of the funnel out. Thank you to your wearing protective gear. Tighten up, Deech. You got it. Oh, man. Yeah, I might as well let you guys see what I'm doing. I mean, I'm just trying to pull out some of the extra alcohol with I don't want all that alcohol in there. So I'm just pulling a little extra out. I'm going to have to, I think just 2 more squirts and we'll be back in business. 1, 2. Okay, so I've got the alcohol and I've got the water. That's all set. And I've got a mess to clean up a little bit later. Okay, so you can kind of see two layers, right? You can see sort of this alcohol and you can see this water. What I'm going to do now is I'm going to mix it up and we're going to see if we can get that layer to disappear. If that layer disappears, that means that the alcohol and the water mix. You can see you can see that layer right there, right? It's not. See, it's shaking. It's an actual layer. Oh, that's gorgeous. Come on, baby. Anyway, okay, you can totally see that's a layer of alcohol on top of the water. How you doing there, administrator? So we're going to shake this up and see if we can't make that layer disappear. If that layer disappears, then we know that the alcohol and the water mix. Here we go. Let's mix this baby up. And we're going to see if they separate back into two layers. All right, so let's let that set. We're going to let that settle. I see a bunch of bubbles. See all those bubbles? That's because the alcohol and the water actually do mix, and as they do so, the volume decreases. Well, that creates a little bit of a vacuum, and that's where all those bubbles come from. So SS Morgan is saying that layer is coming back, but I hate to break it to you, SS Morgan. I don't see it anymore. Here, I'll zoom in real tight. All right? No layer. See, this is from the bottle itself. Right? That's from the bottle that you see down there. So that's a line on the bottle. Okay. And as we move up, there's no layer. Bester, you don't need to see color to see the layer. There's no layer there. All right. Okay. So we know that the alcohol and the water mix really well. So that means there's got to be some attraction between the water molecules and the alcohol molecules. But here's the deal. Here's where things get interesting. Now what I'm going to do is I'm going to add some salt to the bottle. And here's what salt does. Let's just watch first. Let's just watch and then we'll explain, okay? Here we go. Here's my funnel. In goes the salt. And it goes... And let's see what happens when I add salt. Okay. I see a bunch more bubbles again. Coming out the top like crazy. All right, let's give this baby a shake. Is it sea salt? It's just sodium chloride. Which I suppose, that's not technically sea salt. Sea salt you got to get from the sea, but there's a lot of sodium chloride in, ocean salt water. So I'm shaking this up, trying to get the salt to dissolve, and when the salt dissolves, it forms ions. It'll have sodium ions and chloride ions, because, salt is sodium chloride. So we're going to shake this all up and try to get as much of that salt dissolved as we can. Just a few more shakes, baby. All right, let's see if that works. Let's see if we can see a layer. I see a layer happening. It's a little tough to see, but when we add... Oh, there it is. You can totally see it at the bottom. Pay attention right down here. You see it? See it starting to rise? So this here in the middle is a mixture of the salt water and alcohol. And then down here, the salt water is separating out from the alcohol. Right here in the middle, there's a mixture of the two, and you can see this layer slowly shrinking. So what we have is alcohol up here on the top that's kind of clarified. We have salt water on the bottom, and then what we call is emulsion in the mixture, but the emulsion is disappearing. So you can totally see there's two layers. Now, the reason why this happens is because the salt ions and the water molecules are so attracted to each other that they, molecularly speaking, they date exclusively. So their attraction is so strong that the alcohol can't compete and it gets pushed out. Now, the alcohol is less dense than salt water, and that's why it floats on the top. Isn't that cool? Isn't that interesting? So we call this effect salting out. It happens with mixtures of water and alcohol and other organic liquids, that mix with water. You can salt them out. So how does sodium, an explosive element in air, and chlorine, a poisonous gas, make a salt? Bester, let me answer that question while I put some universal indicator in here so we can see the layers a little better, okay? Actually, I think I'll do purple food dye instead, okay? And we'll zoom in on it so we can, thank you there, Weeb. We're going to put in some purple food dye. I'm going to zoom in here so you can see because it really looks beautiful. So here's the deal, Bester. Sodium can take different chemical forms. Sodium metal that's the metallic form of sodium. In goes the purple food dye. Look at that. What gorgeousness. So sodium metal is chemically different than sodium ion. Sodium ions have a positive 1 charge. All of the atoms in sodium metal are neutral. They are chemically different, chemically distinct from one another. Therefore, they have different chemical properties. The same is true with chlorine. When chlorine becomes an ion, it gains negative charge. It becomes the chloride ion. So chlorine atoms with a negative charge are chemically different than the element chlorine. The element chlorine actually exists as molecules. We call that chlorine, or Cl2. And Cl2 has different chemical properties than the chloride ion. Okay, so we're going to back this out so we can tell. Let's recap where we are here. Where we are here is we have a mixture of salt water on the bottom. That's down here. We've got alcohol on the top. Hey, come on, Nabeen. I appreciate that. Nabeen Gab, I love your content since day one, never stop. Come on, man. I appreciate that. It's not necessary, but it's helpful. It's helpful to get these gifts to, I do have to purchase quite a bit of stuff to do these. I really appreciate that, Nabeem. I like your comment. Since day one, never stop. Come on, Nabeen. Nabeen Gabriel, M7. I apologize if I'm saying your name wrong. I appreciate the gift. Very, very much appreciated. So back to what we're doing here. We got salt water on the bottom. We got alcohol on the top. And to the top layer, I have added some violet food dye. We're going to give this a shake, okay? We're going to give this a shake. And everyone give a like to Nabeem Gabriel, who sent me a gift, which is much appreciated. Let's shake this baby up, see what happens. So when it goes, we're going to shake this up. Is this toxic? Only because of the isopropyl alcohol. Okay. Come on, baby. There it is. Look at what's going on. Ha, I love it. So the purple dye actually has a pink dye in it, which goes in the alcohol, and a blue dye in it, which goes into the salt water. And what I love about this is you can now see the 3 layers very easily. The alcohol layer, the salt water layer, and what we call the emulsion. The emulsion is a mixture of the alcohol and the salt water. You can see it doesn't last forever. It's a transient mixture. Dynamic kinetic art, baby. Come on, PSI. Let's add a little more. I love it too. Let's add a little more dye here, okay? We're going to add a little bit more dye. I'll zoom in on it because I want to get that blue really vibrant down there on the bottom. Let's do some art, man. Here we go. Let's zoom in here. Okay. Zoom in. I want to see that purple dye going in there. Let's add a drop here. Boom. Look at that. Come on, man. That's just beautiful. That is just gorgeous. All right, let's add another drop. Here we go. One more. Boom. I love it. Absolutely love it. There you go, Sodi. We got more dye. We got more dye. All right, let's back it off. Hey, Jingling, thank you. Thanks for coming on board and checking out the channel. I appreciate it. So basically, sodium ions crush the chloride ions and make mini explosions and turn atom dust that makes salt. So basically, Bester, what happens is sodium metal atoms react with chlorine molecules, and that makes sodium ions and chloride ions, and the sodium ions and the chloride ions mix together to make sodium chloride, which is salt. I'll say that one more time. Sodium atoms, which are neutral, electrically neutral, react with chlorine atoms, which are chlorine molecules, which are electrically neutral. Those react, and you get sodium ions that are positive, chloride ions that are negative. Those positives and negatives attract over and over again, and that makes a salt crystal. I would 3D print an enclosure around a round vial of it and rig it to a button to dispense dye. That's cool there, PSI. Very cool, man. Very cool. So Bester, just to give you, I can draw it out in a chemical equation if this might help. Give me a second here. I'll write it like this. So sodium solid, like that. Okay. That's neutral sodium metal. That's the stuff when you put it in water, man, that stuff explodes. Okay? That's going to react with chlorine gas. So there's a bunch of chlorine molecules, chlorine molecules that are all made by two chlorine atoms stuck together. Those are going to be in the gas phase. Now these react, and they form, I got to balance everything, so I'm going to do this. So they're going to react, and they're going to form a solid, sodium chloride, and this is a solid. Now here, the sodium ions in the sodium chloride are actually sodium ions, Na+. Up here, they're neutral, and the chlorine is actually the chloride ion, that's Cl negative. Up here, the atoms are neutral. Here, they have become ions that are negative. Sorry there, Sodi. If you have questions, you can certainly give me an ask. Well, I got a mess here, folks. I made a mess. Look at all that stuff down there I got to clean up. Is the salt solution super saturated? Nabeem, so, all right, we can do it one more time, Nabeem. We'll do it one more time, all right? This one's for Nabeem. Let's go one more time. And then I'm going to turn the camera around. I'm going to talk to folks, okay? So we got one more experiment we're going to do, and I'm going to call it quits for the day. I'll do some talking to you. I'll flip the camera around. We'll chat, and then, I'm going to call it a day. So, Nabeem, here's the way this works. I have some water in this bottle. To this, I'm now going to add some isopropyl alcohol. So this is the way the whole experiment works. So in goes my funnel. I'm going to add some isopropyl alcohol. Sodi, usually around this time. So usually like now or maybe roughly an hour later. I got to add a little more isopropyl alcohol. Excuse me a second. Let me open this second bottle up. All right. This effect that I am demonstrating, we call it salting out. All right, let's add a little more. In goes the alcohol. We're going to stop right there, okay? Boom. If you look closely, you will notice that the two currently don't look like they mixed. So you might see a small separation between. Yeah, this is all at room temperature. All right, let's look here. Well, there it is. Well, no, I actually can't see it this time. I think there's some good mixing going on. Yeah, there it is. There's the layer. You can see it right there. You see that? See that? You can see there. Okay, that's gorgeous, man. So we got the water down here, and we got the alcohol up here. And, if you just kind of pour them in quickly, the two layers kind of stay separate. But what we want to do is we want to really mix this up well to see if those two layers will separate out again. So that's what we're going to do, okay? Yeah, that's beautiful to see. It's like a little cloud or something. Anyway, we're going to mix this up. Remember, what's in here is alcohol and water, so let's mix it up. All right, here we go. Shake that up, and we're going to see if the alcohol and the water separate into two layers or if they're going to just completely combine. All right, so there we go. What do we got? There might be a layer there, huh? There's a bunch of air bubbles, and those air bubbles are actually signifying that the two are mixing, because when they mix, the volume goes down, and that makes a vacuum. That's what we're seeing, all those bubbles. So the water and the alcohol, they mix together well enough. They're attracted to each other well enough, the molecules are, that they actually do combine. So that's what, we say there are intermolecular attractions. There are attractions between the water molecules and the alcohol molecules, and that's why they combine into a single layer. There's a single layer, right? We don't see that wavy line anymore. It's one singular fluid. And we can test this by adding some food dye, which I'm going to add. I'm going to add some purple food dye to this, okay? Then goes a couple drops. So we got to watch this, though. This is just fun to do. We're going to add purple food dye, and we're going to watch. Here we go. Boom. Isn't that gorgeous? So it is now completely mixed. There is no separation. And if we leave it undisturbed, that separation, the mix will stay mixed. When you buy isopropyl, it usually comes in a mix of 90 or 70. Does that mean no, it does not separate, Jingling. It's like this. It's completely mixed. So if you take a drop of food coloring and you drop it into your bottle of 90%, it's going to do this, right? It's going to go all the way through because the alcohol and the water are completely mixed. So we say that alcohol and water are miscible, okay? That means they mix in like all proportions. So long there, SS. Great having you on board. So PSI means if I leave it unmixed. So PSI, if you leave it unmixed, if you wait long enough, it will mix. How long will it take? That depends on a lot of different conditions like temperature, how often you bump into it, a lot of different things. But it ultimately will completely mix. All right? So Bester, it would explode if you added it to a mixture of water and alcohol. I've done it before. You got it, Jingling. Okay, now what we're going to do is we are going to, I think it would actually react with the alcohol to begin with. All right, now what we're going to do is we are going to add, well, let me mix this up here so you can see it actually is mixed. Let's do this first because, it doesn't look like the dye is completely spread out. So let's make sure the dye is spread out. Mix it up so you can see, okay, that baby's fully mixed throughout there. Now the next step is to add some salt. So this is a mixture of alcohol and water. We're going to add some salt to it. Here we go, baby. Where's my funnel? This is tough to do without the funnel. In goes the salt. Now what happens now is the salt is going to dissolve into the fluid. That's going to release sodium ions and chloride ions. And the deal is those sodium ions and those chloride ions, they are more attracted to the water molecules than they are to the alcohol molecules. And what actually happens is the water and the ions, they are attracted so strongly to each other that what I like to say, they date exclusively on the molecular level. So, just like when two people date exclusively because they're so strongly attracted to each other, that's basically the way it works. The same thing happens with molecules. In this case, the salt and the water are going to date exclusively, so to speak, and that means the alcohol is going to get pushed out, right? The alcohol cannot outcompete the salt for the attraction of the water, and that means the alcohol is going to get pushed out. Let's watch it happen. Give it one more good shake. Pop that on there, and let's see it go, baby. Come on now. There it's going. I can see it. So if you look up at the top, you can see the alcohol layer. The pink dye from the purple dye ends up in the alcohol layer, and the blue dye from the purple dye ends up in the saltwater layer. So the salt ions and the water are finding each other and dating exclusively. Here in the middle, there's a mixture of the alcohol and the salt water. We call this the emulsion. The emulsion will not last forever. You can see it shrinking. What's it shrinking into? Well, the alcohol layer and the saltwater layer. Bromine gas is made of Br2, bromine molecules. It's like an alien sunset. Probably a little bit, wee blue. Probably a little bit. But I've not done the experiment to find out. But if I remember correctly, there's going to be a little bit dissolved in there. So, you know, I'm simplifying. Everything's a bit more complicated than I'm saying, but at least it gives you the idea. The basic idea, yeah? All right, fair warning. It's time for me to flip the camera around. You get to see an old man in his basement. If that's not something you want to see, you're going to want to get out of here. I'm just warning you right now, okay? Might not be something you want to see. Here we go. So, Nabeem, what you're going to want to do, 240, this is a half-liter container, 240 milliliters of water. It's about 280 milliliters. You got to make sure you're paying attention here, of 90% isopropyl alcohol, 91%. So again, 240 water, 280 of 91%. Don't get 70, get 91%. Mix those up, and then you're going to add about 60 grams of salt. Hey, everybody, drop your favorite element in the chat. Looks like Bester's favorite element is bismuth. How's everybody doing out there? We had a good time today, man. I had a great time. I don't know about you. Let's get this light on here. There we go. Talk to folks. How's everyone doing? Looks like Nebox likes uranium. Thanks, Sarah Moobs. Diva likes samarium. My favorite is hydrogen. Love hydrogen. Come on, Weeblue. Right there with you. Loving some hydrogen. PSI likes oxygen. Pounds per square inch, huh? Hello there, Richmore family. That's a nice one, VK. Gold. Carbon. Yep, carbon's a good one. Most folks like carbon. Pretty close, Nabeem. Pretty close. You're going to change that to 280 milliliters of 91% isopropyl. Shelf life, this lasts a good long time, Nabeem. That'll last you, the bottle will weaken from the alcohol dissolving it before anything else goes. Water stuff in Dutch. Oh, is that how, that's cool. Carbon dioxide, the Richmore family, given a favorite compound. I think I'm with you. It's my favorite compound too there, Richmore family. And I have some for you. Let's check it out. I got some carbon dioxide for you. We did a little experiments with it a little earlier today. Let me show it to you. I was messing around. I'm telling you, I got this new experiment I'm doing with carbon dioxide. I can't wait to show it to you. I don't know when it's going to come out. Hopefully I'll have the video edited soon. Yeah, a little dry ice, huh? A little bit of dry ice. So I was messing around with this today. Might as well put a little bit in a little bit of water. Just make it look sciencey, because, you know, that's what we do around here. We try to have fun with science. So give me a second here. Let me find my, find a container. Oh, put a little water in here. Have a good old time with some dry ice, baby. Oh, I love it. I just love it. Oh, it's so beautiful. It's just fun. It's fun. Manerjack, because purified 70% isopropyl. Well, I don't know about dropping a match head into some alcohol there, John Doe. Hey, there you go. I am Nabeem. You don't have to worry about this that much. I use this all the time. If you use liquid nitrogen instead of water in the same experiment with the alcohol, what would happen? Well, you sure wouldn't want to seal up the bottle. Not with liquid nitrogen in it. And me too, the Moore family. It went poof. What is sodium? It's a silvery metal that's can be cut with a knife, and when you drop it in water, it makes sodium hydroxide. Yeah, very cool. Well, hey, folks, I had a good time with you today. Thanks for hanging out. We did some cool experiments, enjoyed some time together. Yep, I got to go too, Rich Moore. Yeah, we did some stuff with some dry ice and some colors and all sorts of good stuff. I had a good time. So, hey, how can you chemically make sodium metal from sodium salt? So, John Doe, my understanding is that you melt the salt by heating it, and then you run electric current through it. And then you got to be careful with that because you're going to make chlorine gas at one of the electrodes. So it's nasty stuff. And then, of course, you make sodium at the other one. Hey, thanks there, Jingling. I appreciate that. My hat's off to you, bud. I appreciate that a lot. So, yeah, we had a great time today looking at some beautiful phenomena. And you know what? Just, it's always there. I mean, you can just pay attention to the world around you. There is so much to see and explore in like every single moment. The sun rises, the sun sets, you're looking at the grass, you're smelling the mowed lawns, you're petting your dog, whatever you're doing, man. There's just all these beautiful experiences that we can see and taste and touch and smell. The universe really is a beautiful place. And I'll tell you what, for me, when I understand some of the science behind the phenomena that I'm seeing, the universe gets even more beautiful. So thanks for hanging out with me today, checking out some of the beauty of the universe, and hopefully I'm going to see you next week. All right, folks? Thanks, John Doe, and we'll see you next time.